Hi there. In this video, we are going to talk about the gambler's ruin problem. This is an example of an absorbing state Markov chain. This gambler's ruin problem tells us something very significant and also something very shocking. What it tells us is that a gambler will always ever end up going broke, will always ever end up with nothing under a certain set of assumptions. And these assumptions are not far removed from reality. We're going to go through each step of these assumptions and how they come about and how they lead to this conclusion, and also why they're not far removed from reality. Just as a general overview of what those assumptions are, we would say that if the gambler keeps playing long enough for an extended period of time, which can be analogous to many years, playing at a casino for many years. Another one of those general assumptions is that this casino has a large amount of money. It has nearly unlimited wealth. And also, another assumption is that the game is unfair. So we're going to put this down in mathematical terms and explain how we end up with this particular conclusion. So we're going to start off by saying that the gambler has some amount of money right now. We're going to say that the gambler has a current fortune. So this is the current fortune of the gambler. And we're going to say that it is I dollars. And we're going to say that I is going to change, and it's going to end up between 0 and n every time the gambler plays a game. And this capital letter N represents the goal of the gambler. The gambler wants to end up with a certain amount of money. Maybe his target is $1 million, $100,000, or whatever is the case. So the gambler is going to play and is going to end up between these two states. So every time the gambler plays a game, so the gambler is going to play a game, and when he or she does that, they're either going to win $1 or lose $1. So we're going to say they either win $1 or they're going to lose $1. So if they win $1, I will essentially go to I plus 1. Or if they lose $1, I is going to go to I minus 1. So we're going to say that the probability of winning $1, so that would be P, so we can designate that probability by P. And therefore, what it means that the probability that the gambler loses $1 is 1 minus P. And we're going to call that Q. So Q is equal to 1 minus P. So the gambler is going to stop. So these two states, 0 and n, they represent two n points. So the gambler would stop, and this would correspond to I being 0, or they reach the goal. And that would be I is equal to n. So the states of the Markov chain, which is how we're going to model this whole thing, is by using the amount that the gambler actually has. So when we talk about the states, we're talking about the amount of money that the gambler has. So the states would basically be the set of numbers that would be 0, 1, 2, and all the way up until n. So as we said just now, I is equal to 0 corresponds to state 0. And I is equal to n. N corresponds to state n. This means that the gambler has reached the goal. So another thing that I want to say here is that states 1, 2, all the way till n minus 1 are transient states. So when you say transient states, we mean that they are changing. So transient means that it's changing states, and they would essentially correspond to the states of 1, 2, all the way to n minus 1. So we say that they are transient because the gambler would either stop when I is equal to 0 or I is equal to 1. So if the gambler has either between $1 or n minus $1, it means that the gambler would continue playing. So because he or she would continue playing, it means that these are transient states. So now that we know what the transient states are, we can go ahead and write what are the transition probabilities. So we can talk about the transition probabilities. So we can write it as capital letter P, which is the transition probability, and we use two subscripts, 0, 0. So this 0 represents the current state, and this other 0 represents the future state. So if the gambler has nothing, what is the probability that they will have nothing in the future? So we said that the gambler stops playing either when state 0 is reached or state n is reached. So if they have currently ended up with 0, then they will not keep playing. So this transition probability is equal to 1. Similarly, if the gambler has reached their goal, then they're not going to play afterward. Then it means that this transition probability is also 1 because the future state is also n. So if we are in state 0 or if we are in state n, then it means that the gambler would remain in that state forever. So this is actually what is meant by a absorbing state Markov chain. So if you go up, you can see that we said that the gambler's ruin problem is an example of an absorbing state Markov chain. So an absorbing state Markov chain means that once a certain state is reached, whatever is happening would not move out of that state. So if that gambler is in state 0 or state n, they are not going to move out of those states anymore. So that's why it's called an absorbing state. So the rest of the transition probabilities, so if we are in state I and going from I to I plus 1, we said that the probability is p. So that's a small letter p. And then the transition probability now of being in state I and then losing $1, so going from I to I minus 1, we said that this probability is q, where q is 1 minus p. So we can represent these transition probabilities in terms of the Markov chain. So we can write out our different states. We have state 0, and then we have state 1, we have state 2, and just a reminder that these states are the amount of money that the gambler has. And then this goes all the way to state n minus 1. And then lastly, state n. So what we have said is that if the gambler is in state 0, then they remain in state 0. And similarly, if the gambler is in state n, then the gambler remains in state n. And these probabilities are 1. So if the gambler has $1, then the probability of losing that $1 is q. And the probability of gaining $1 is p. Then if the gambler has $2, then the probability of losing $1 is again q. So we can write the rest of the Markov chain like that. And then the probability of going from n minus 1 to n is p. And it remains like that. So you can see that how it's a absorbing state Markov chain is because there is no transition probability from 0 to 1, and there is no transition probability from n to n minus 1. We can now proceed to set up the transition matrix using this information. So our current states, you would recall that we write it as the rows. So the rows represent the current state, and the rows could be 0, 1, 2, and so on. All the way to n minus 1 and n. And the columns of the transition matrix, this would be our future states. So our future states would be 0, 1, 2, all the way to n minus 1, and then n. So if we are in state 0, the transition probability of remaining in state 0, of going from state 0 to state 0, that probability is 1. And then the probability of going from state 0 to state 1 is also 0, because we know that it remains in that state. Similarly, the probability of being in state n and remaining in state n is also 1. So we have current state n, future state n, and the rest is zeros. We can write zeros from there. Now we can look at being in state 1, the probability of going from state 1 to state 0, so that we set is q. Then we have 0. Then we have the probability of going from state 1 to state 2, that probability is p. And the rest would be zeros. Then the probability of being in state 2 and then going to state 0, so that by definition, how we have defined our assumptions, we said that we cannot go from state 2 to state 0. We can go from state 2 to state 1, and that probability is q. And the probability of being in state 2 and going to state 2, that's also 0. And then, of course, we can have state 3 here, and then state 3, that would be p. So maybe we can just write 3 here, and we can write p here. We can see that there is obviously a trend developing here, where we're having p's going along the diagonal, and then the probability of going from n minus 1 to n, that probability is p. And then the probability of n minus 1 to going from n minus 2, so that's going to end up being q on this diagonal as well. So from n to n minus 1. So yeah, we can write it like this. Sorry, from n minus 1 to n minus 2. So we can write q here somewhere, maybe. So the rest would be zeros everywhere else. So this is how we would set up our transition matrix. Okay, so now let's move on to actually deriving and solving the gambler's ruin problem. So we're going to start by asking a question, and that question is, what is the probability of reaching n? So regardless of what the gambler starts out with, what is the probability of reaching the end goal? So we're going to start off by defining HI. So this HI represents the probability that the gambler hits n or reaches the target n before going broke while starting with I dollars. So HI is the probability of achieving the target n before going broke, before achieving nothing, while starting with I dollars. So that's what the subscript I represents. And previously we said that P is the probability of winning $1 with each play, and Q is the probability of losing $1 with each play. So let's just remind ourselves of the multiplication rule. So if we have event A happening, and it has a probability A, so P of A. So given that A occurs, event B happens with probability P of B, given that A has occurred. So we have this line and this A to represent that. Event B occurs only if event A occurs. So then we say that what is the probability of P and B occurring? And that's equal to the probability of A multiplied by the probability of B, given that A has occurred. This is conditional probability. So a simple example of this would be if you have a bag and you would draw a marble from the bag. And if the marble is a certain color, then you flip a coin. So let's just say if the marble is red, so we have a red marble, and this corresponds to event A, and this is equal to 0.4. And then we said if we draw this red marble, then we will flip a coin. So of course, you can get either heads or tails. So let's just say we get heads, and this corresponds to event B. And this has a probability of 0.5. So what is the probability of getting a red marble and getting heads after you thereafter flip the coin? Well, that would be just 0.4 times 0.5, and that's equal to 0.2. So this is important to understand when we're going to derive this gambler's ruin problem, as you will now see. So let's just say, going back to the gambler's ruin problem, and we say that I, and let's just say I is equal to 1. So the gambler is starting off with $1. So let's just say now that N is equal to 3. So the target is $3. So we can represent this with a tree diagram. The gambler is starting off with $1, and the gambler can go to $2 with probability P, or can go to nothing with probability Q. So if the gambler now has $2, the gambler can now go to $3, or can go back to $1. So again, that is P, and that's Q. So we must understand that if we end up here with $1, this entire tree at this point is going to look exactly the same as it is when we had started. So everything after this initial $1 here can be replicated at this point, because remember that this entire process is going to repeat itself. So you'd remember that we had defined H. We just go up here to H, and we said H represents the probability of hitting the target while starting with I. So we can have H1, H2, and H3. We can even have H0, but we know that H0 will equal to 0. So this H0 will equal to 0 because you cannot reach the target if you're starting from 0. Remember that this is an absorbing state Markov chain, and if you start at 0, you will never ever hit this target of 3. Similarly, the probability of H3 is equal to 1 because you have already reached the target. So remember that H represents, let's write it like this. So HI represents the probability of eventually reaching N, given that you have started with I. So that's very important to understand. So we can write equations for H1 and H2. So what is H1 equal to? So H1, we remind ourselves, so this is 1. So H1 is the probability of reaching $3, given that we had started off with $1. $1. So this would firstly be the probability of reaching 3 from 0, because this is this branch of the tree. So it would correspond to Q times H0. But we know that H0 is equal to 0, since there's no way of reaching 3 from this particular branch. So anyway, then it is the probability of reaching 3 from 2. So the probability here of going from 1 to 2 is P, and we can reach 2, so this is H2. So the probability of reaching 3 from state 2. So in other words, what we've done is added the probabilities of the two branches. Similarly, H2 is equal to the probability of going from state 1 to 3. Remember that this entire branch replicates itself. So we're going to have Q times H1, then plus P times H3. So let me just say that once more. H2 is equal to, firstly, the probability of reaching 3 from this first branch, and that's Q times H1. Remember that everything from this point is the same as that point, plus the probability of reaching state 3 from 2. Well, that's a guarantee, because H3 is equal to 1. So we can actually just write some equations and we can completely solve all of these equations, because we can substitute H2 inside equation 1. So if this is equation 1 and that's equation 2, we can substitute H2 inside there. We can say that H1 is equal to Q times H0 plus P into Q times H1 plus P times H3. So this equation actually corresponds to just adding up all of the branches. Q times H0 is that branch, then P times Q times H1, P times Q times H1, P times Q times H1, so that would correspond to that term, then P times P, so that's P times P, times H3. So that branch plus that branch plus that branch. 3 terms, 1, 2, and then 3. 1, 2, 3. So if we just say that P is equal to 0.5 and thereafter Q is equal to 0.5, so we can completely solve this. So we'll have H1 is equal to 0.5 times 0. Remember that there's no way to reach state 3 from 0. Then we have 0.5 times 0.5 times H1 plus 0.5, I'll just write squared because that's what P times P is, and times H3. And H3, we know that it's equal to 1. So we can solve for H1 inside all of this, and we can see that H1 is equal to 0.33. So in other words, there is a 33% chance of reaching your goal of $3 if you start off with $1. And if there is an equal chance of either winning or losing. So let me just say that once more. if you have an equal chance of winning or losing, that's P and Q is equal to 0.5, then the chance of reaching $3, if you start off with $1, is just 33%. Okay, you got a 33% chance of reaching your goal. So how can we generalize this? Can we come up with general equations? And that's actually what will tell us how we actually show the gambler will actually go broke under these certain assumptions. So we're going to take this specific scenario and then generalize it in terms of the equations, and then we're going to end up with the conclusion that we had started this video off with. So we begin by writing a general expression for HI. You can see here that H1 is equal to Q times H0 plus PH2. We explained how these relations come about using the tree diagram. So if we were to generalize this and write it for HI, then we can see that we can write it firstly in terms of P and Q. So we'll just take the P term first. So we've got P, and this H2 would correspond to HI plus 1 because we have a 1 here. 1 plus 1 is 2. So we have here I, then we just have I plus 1. Similarly, we have Q, and the H0 would be analogous to I minus 1. So this is the relation we're going to work with. I'm just going to take that down and rewrite it. So we have HI equal to P HI plus 1 plus Q HI minus 1. So I'm just going to take the HI to the other side. If I do that, I get P HI plus 1, that's that term. Then we have plus Q HI minus 1 and minus H1, sorry, HI. So in front of the HI, there's 1. We can replace that 1 with P plus Q because we know that probabilities must add up to 1. So this is just a trick that's been done here. So I can expand out what is inside this bracket. And then if I do that, I get PHI plus 1. And then if I expand out that bracket, I get minus P times HI. I'm just writing it first here. Then I have plus Q HI minus 1. And then I have minus Q times HI. And this is equal to 0. So what I'm going to do is take the P as a common factor and also the Q. And then I'm going to send the Q term to the other side. So if I do that, I get P into HI plus 1 minus HI is equal to Q. And then since I've taken it to the other side, the signs change. So I write HI first, and then I have minus HI minus 1. So that's minus 1. So this HI minus HI minus 1. Let me just write it. HI minus HI minus 1. This is actually what we call the forward difference because this is a recurrence relation. So we're going to call it DI. So DI is equal to HI minus HI minus 1. So for example, if we say D2, then we actually say H2 minus H1. Or D1, which is H1 minus H0. HI minus HI minus 1 equal to DI. So we can replace this. We can say that P times DI plus 1 is equal to Q times DI. So what we have is DI plus 1 is equal to Q over P times DI. So what this is actually saying is that all successive differences are basically in a geometric progression. So it's a geometric progression. Let me show you what I mean. If we write d2, so we've said here that di plus 1 is equal to q over p times di. So if I plus 1 is 2, in other words, I is equal to 1, then what this is equal to is q over p times d1. Then we can say that d3 is equal to q over p times d2. However, d2 is equal to q over p times d1, so we can replace that. We can say that d3 is equal to q over p into q over p times d1. So this means that d3 is equal to q over p squared times d1. So we can generalize this again. So we can say, for example, d4 is equal to q over p cubed times d1. So if we do proceed to generalize this, then what we have is di is equal to q over p to the power I minus 1 times d1. We can also write it for the nth term, or where n is our goal, or the gambler's goal. So that's equal to q over p to the n minus 1 times d1. So what we're going to do now is write an expression for hi in terms of all of these differences that we have just written. So we can say that h1 is equal to h0 plus h1 minus h0. Of course, the h0 minus h0 is 0, so we're left with h1 is equal to h1. But we can write this as h0 plus d1. Remember that di is equal to hi minus hi minus 1. We had seen this earlier. So we can write this for h2. We can say that h2 is equal to h1 plus h2 minus h1. So this h2 is equal to h1 plus d2. However, we already have something for h1. So we can take h1 and then put it in there. So we have h2 is equal to h0 plus h1, which is h0 plus d1. Sorry. h0 plus d1, then plus d2. So we can spot a trend occurring here. Similarly, h3 would equal to h0 plus d1 plus d2 plus d3. So if we generalize this for hi, then we can see that this is equal to h0 plus d1 plus d2 all the way plus di. So this is just equal to h0 plus the sum of dk, where k starts from 1 and goes all the way up until I. So we know that h0 is actually equal to 0. If you go all the way up, you can see that I had explained how h0 was equal to 0. h0 is equal to 0. So this h3 was equal to 1 because n was equal to 1. So we can say here that hn is equal to 1. So we go all the way back down and we substitute that. We can say that hi is equal to, well, this h0 is equal to 0. So we have this sum of dk, but we saw here that dk or di, whatever, was equal to q over p to the I minus 1 times d1. So we can just substitute that in. So we get this d1 that's appearing there. Then we have this sum of q over p. Okay, let me just write it in the next line. We have hi is equal to d1 times the sum of q over p to the power k minus 1, where k starts from 1 and goes all the way up until I. So in order to solve for hi, which is the probability of reaching a certain goal n, is merely this geometric progression, which is what we've shown here. So to find a general formula for this, all we have to do is solve this equation. So writing this a bit differently, we can say that hi is equal to d1 times the sum. I'm just changing the boundaries of the sum. I'm just going to say q over p, and I'm going to say to the power k here. And I'm going to say that k now starts from 0 and goes all the way to n minus 1 or I minus 1. So it's the exact same sum. I've just changed the bounds. So we need to solve for d1. So how we're going to solve for d1 is by using some boundary conditions. So firstly, we're going to write this expression for hn. And if we do that, we see that we get d1 multiplied by the sum where k goes from 0 to n minus 1. And we have q over p to the power k. So what we should remember here is that we derived an equation in high school probably, where we saw that if we have the sum of a geometric sequence or series where k goes from 0 to m, and we have r to the power k, and r was this ratio, then this is equal to 1 minus r to the power m plus 1 divided by 1 plus r. I'm not going to derive this equation now because this is something that has definitely been covered by most people in high school. So you can just refer to another textbook or something like that to understand how this is derived. So we can now proceed to calculate d1 because we said that hn is equal to 1. So we have 1 is equal to d1, and then just applying this formula, we have 1 minus q over p to the power n divided by 1 minus q over p. So what this means is that d1 is just equal to 1 minus q over p divided by 1 minus q over p to the power n. Just swap around the numerator and denominator. So we can now proceed to determine hi. So we said that hi is equal to d1. So d1 we have now determined that. 1 minus q over p all over 1 minus q over p to the power n. So this is multiplied by this sum. So there's a here. So we can just use this formula and apply it to the sum as well. So when we do that, we get 1 minus q over p to the power I divided by 1 minus, that's 1, so that's 1 minus q over p. So this 1 minus q over p and 1 minus q over p just cancel out. And then what I'm left with is 1 minus q over p to the power I divided by 1 minus q over p to the power n. So this is for a very specific case. So this case is specifically, we write at the bottom, we'll call it case A. So this is where we are assuming that p and q are different values. For example, p is not equal to half. If p and q are just the same, if p is equal to half and q is equal to half, then you can see that this equation doesn't really apply. So what we're assuming here is that r is not equal to 1, where the r in this equation refers to this particular r. So on the other hand, we can consider another case, case B, and this is where p is equal to a half. In this case here, r is equal to 1. So if that's the case, it becomes quite easy. You would remember that we saw earlier on that we had p di plus 1 is equal to di times q. So if p and q are equal, then it means that di plus 1 is just equal to di. In other words, the forward differences are just the same. Okay, so if that is the case, then what this means is that hi, it just depends linearly on I. Again, this is something that you would have done in high school. For example, 1 plus 2 plus 3 plus 4 and so on. And if we wanted to find the sum of this, well, we have the differences between the different terms, and you can see the differences are the same, which is what we're actually talking about here. And we can see that we can predict the next number because it linearly depends on its position. So I'm not going to get into all of this, but in any case, we can say that hi is equal to ai plus b, where just a and b are two coefficients. In the same way, here you can say that t at n is equal to an plus b. So we can solve for A and B quite easily, and we can do that again using the boundary conditions. We can say that I is equal to 0, and then we have H0 is equal to A times 0 plus B, and we already said many times now that H0 is just equal to 0. So this is equal to 0. So what this means is that B is equal to 0. Similarly, we can consider where I is equal to n. Therefore, what we have is Hn is equal to A times n. Since B is equal to 0, we don't need to include it. And we also said many times now that Hn is equal to 1. So what this means is that A is equal to 1 over n. So our general form of the equation is that Hi is equal to I over n. And this actually corresponds quite well with what we had seen earlier. Remember that we said that I is equal to 1 and n is equal to 3 when we drew the tree diagram earlier. You can just go back up and check it if you would like. But in any case, what we said that you would remember that H1 was equal to 0.33 if you go back and look at the tree diagram. So we can just use this formula. Okay, what is the probability of reaching $3 if you start off with $1? In this case, I is equal to 1 and n is equal to 3. So that's how we get 1 over 3, which is 0.33, so on. So before we conclude, we actually need to see how the gambler ends up with nothing. So how do we do that? Well, we can go back up and look at this case A where P is not equal to half. So we can take this equation that we've just derived here and we can consider when n approaches infinity, when n is a very large number. So in other words, the gambler sets a very large target. So he wants to become rich. He wants to have $1 million or hundreds of millions of dollars and so on. And we assume that the gambling establishment, like the casino, has sufficient money present there at any given time so that theoretically this can be reached. So let's just say that n does approach this very large number. So let's consider where P is more than a half. So if P is more than half, then what do we get? We have Hi. Well, let's just see. N approaches infinity. So if P is more than a half, it means that Q is less than a half. So Q over P is less than 1. It can only be between 0 and 1 because P will always be less than Q. So we have a decimal number raised to a very large number. So that's just going to approach 0. So this term is going to approach 0. So we have just 1 in the denominator. So this means that it's going to equal to 1 minus Q over P to the power I. Okay, so this is actually a good scenario. So what this says is that if the chance of winning a game is more than half, okay, if there's a greater than 50% chance that the gambler will be able to increase his total at that given moment in time by $1, it means that after a long time, okay, there is a positive probability that the gambler will be able to achieve some significant amount of money, okay, some large total. There is a positive probability of doing that, but only if the game has a more than 50% chance of winning. On the other hand, let's consider what happens if the probability of winning a game is less than 50%. So it means that the probability of reaching the goal, which is what H actually represents, Hi, let's see what happens. We have, again, Q over P. So P now is less than half. So Q is going to be more than P. So Q over P is going to be a number greater than 1. So you have a number greater than 1 raised to the power infinity or a very large number. So that's going to be, where basically we can say that we have a very large number in the denominator. So we can say that this entire Hi is just going to approach 0. So this is the gambler's ruin problem. This is why when we started off the video, we said that the gambler's ruin problem, there's a reason why it's called the gambler's ruin problem. What it means is that the gambler will always ever go broke, will always ever end up with nothing. There is a 0% chance. There's a zero probability that the gambler will be able to get rich. Okay? If any game that he plays for a long period of time has a less than 50% chance of winning. That's essentially what it means. So in the course of this video, we have covered quite a bit of information. We have started out by modeling this entire gambler's ruin problem as a Markov chain. We defined what the states are. We showed what it looks like when we draw the chain, when we set up the transition probability matrix. And then we proceeded to create this recurrence relation, and then we solved it and ended up showing exactly how it can be the case that the gambler has no chance of actually getting rich and of losing everything if it is the case that the game that he is playing has a less than 50% chance of winning. So thank you very much for watching.